Welcome. This video is going to continue to talk about emission spectra and how that ties in with physics and energy, and specifically look at Bohr's work with these ideas. So Bohr worked mostly with hydrogen. It's a gas, it's easily available, and he noticed that hydrogen has a discontinuous spectra, which means only certain frequencies of light were being emitted. So there's lots of black or blank spots, when normally a continuous spectra looks like the rainbow. So a discontinuous spectra is when only certain colors show up in that spectra. So you could kind of think of it as looking like a colored barcode, and in a moment here I'll show you what hydrogen spectra looks like. So when Bohr noticed that not all the colors are being represented or emitted, he proposed that electrons have a normal state or a normal place or area in the electron cloud where they typically hang out. And this normal state requires the least amount of energy, and he called it the ground state. He also thought then an electron could gain enough energy to move to a higher energy state or further out in the electron cloud, and he referred to that as an excited state. So I like to think of states, ground state and excited states, kind of being like on a swing. If you think of the nucleus as being the top of the swing, or where the swing is anchored, on the left side here, this is a very short swing, so it doesn't take much energy for this child to move back and forth, but then she also doesn't get very far away from the center. But on the slide on the right, these swings have much longer chains on them, so it takes more energy to get them going, but then they also swing much further away from the center. And just like it takes more energy to get these swings going, it takes more energy to stop them as well. So keeping this in mind, what Bohr said is when an excited electron drops from a higher energy orbit to any lower energy orbit, the extra energy has to be released. And he said it'll be released as photons and color will be emitted. So again, think of the swings. You put energy in to get your swing going, but when you want to stop, you have to get rid of that energy. You have to do something to release the energy. And in the case of the electrons, they release that energy as electromagnetic radiation, and sometimes it's within the visible spectrum, and we actually see the light being emitted. So the energy of the photon, okay, this is the energy that gets emitted, is going to be equal to the difference in the two energy levels. So if it's going, the electron has been excited up to energy level 5, and it's going to drop back down to energy level 4, then it has to emit the difference in energy between those two states. It will also be equal to the energy put into the atom to excite it from those two states, which makes sense. You have to lose the same amount of energy that was originally put in to put it out in that higher state. So if an electron drops further or more energy levels, then more energy is going to be released, and we'll see a higher frequency color. And purple is the highest frequency color we see, and red is the lowest frequency or longest wavelength we see. So Bohr proposed that electrons move around the nucleus in only certain circular orbits. He thought they moved in these predictable circular or elliptical orbits, and he assigned quantum numbers to the orbits. And he said 1 was the smallest, closest to the nucleus, had the least amount of energy, and 7 was the largest and required the greatest amount of energy. And this is what scientists currently think these energy levels look like. They think they're concentric circles around the nucleus that get larger and larger, the nucleus being the orange here. And so you can see as you move further out, the energy level gets bigger, requires more energy. And then on the lower side of the graphic here, the green dots show an electron moving from energy level 2 back to energy level 1. And the energy difference between these two energy levels, that difference in energy has to be released before that electron can be dropped down. And you see that the photon is emitted, and if that's in the visible spectrum, we would see that energy being released. So this diagram shows the emission spectra that just the one electron in hydrogen can emit, because remember, even though there's only one electron in hydrogen, it has lots of options. It could get excited from energy level 1 up to energy level 2, 3, 4, 5, 6, or 7. So then it can also drop from any of those upper levels, 7, 6, 5, 4, 3, 2, back down. And it might not drop all the way from energy level 7 to energy level 1. It might just drop from 7 to 6 or from 7 to 5. So the diagram, the upper diagram on the left, shows the series that we know about for hydrogen. And the one that emits the most energy is when it's dropping from one of the higher levels all the way back down to energy level 1. And that's called the ultraviolet series, or sometimes it's called Lyman series. And then the lowest energy one is when it drops from one of those upper levels and it only drops back to the third energy level. And that's low enough energy that we can't see it. That's off on the low side, or the infrared series, whereas the ultraviolet is too high energy for us to see. And then, kind of like Goldilocks, there is a visible series we can see when hydrogen's electron drops from energy level 7, 6, 5, or 4, it drops back to energy level 2. Then it falls in the range that we can see it. So we see 4 emissions from hydrogen. We see purple emitted when it drops from level 6 to 2. We see more of a blue emitted when it drops from 5 to 2. We get into the green range when it drops from 4 to 2. And then we see the red when it drops from 3 to 2, which makes sense. 6 to 2 is the biggest drop, so we see the highest energy release there, the highest frequency light, which is purple. And then 3 to 2 is the smallest drop, so that's going to be the lowest energy light we can see, which is red. So, like most atoms, electrons have movement between different energy levels from their excited state to their ground state. And they may have some in that release energy we can see, but there will also be some that we can't see. So that has to be detected by other means. So what this all has to do with the quantum is that eventually scientists realized that Bohr's model only worked for hydrogen. And that's because electrons don't actually move in circular orbits, but they do stay in certain areas or energy levels. So Bohr had the big idea right, but he had some of the details wrong. But again, it fits in with Planck's idea of the quantum that an electron's energy is going to be limited to certain values because, again, it has to take a step. It either moves from energy level 3 up to energy level 4 or moves from 5 back down to 4 or 3. But it can't be in between. It has to take a full step or a full quantum. So this new model is called the quantum mechanical model. And the quantum mechanical model just says that there are atomic orbitals or areas in an energy level where you're likely to find an electron or a pair of electrons. But the quantum mechanical model, unlike Bohr, doesn't try to predict or describe the electron's path. We now know that that path is far more random, even though it's somewhat predictable what area they'll be in. But the movement is totally random and unpredictable.